In this final video, we'll take a look at one more example of solving a differential equation with Laplace transforms. So we're going to begin this one much like the other examples. We see that we have dy dt minus e to the 2t equals 0.1y. So we're going to begin with step one, which is to take the Laplace of both sides. So I'm going to take the Laplace of the right, which is the Laplace of dy dt minus e to the 2t. And that's going to equal the Laplace of 0.1y. So because of the linearity property of Laplace, if I have the sum or difference of two functions, I can take the Laplace of each one individually and then combine them. Again, this doesn't work if they're being multiplied because, again, this involves integration. And so when you're integrating a product, you can't just integrate each one separately and multiply them back together. But since we're taking the difference, we can take the integral of each one separately. Here I'm going to go ahead and factor out my 0.1 times Laplace of y. And just as a reminder, Laplace of y, we don't know what that is because we don't know what y is in terms of t. So now we're going to expand these. Laplace of dy dt going way back to our note sheet, our formula sheet of Laplace transforms. We see that the Laplace of dy dt, number 35, is s Laplace of y minus initial condition. And so now we're going to implement that and plug in our initial condition, which is given as 1. So we have s Laplace of y minus, now the Laplace of e to the 2t, the Laplace of e to any at for any constant is 1 over s minus that constant. So since this is a positive 2, we have 1 over s minus 2. And then we can't do anything else on the left. Oops, I did forget a term here. This should be s Laplace of y minus y of 0. S Laplace of y minus y of 0 equals 0.1 Laplace of y. So I know my initial condition, that's given to me as 1. So that's going to be a 1 right there. And now I want to move to step 2, which is to isolate Laplace of y. So I have two terms on the left that don't belong there, that don't have Laplace of y in it. That's the minus 1 and the minus 1 over s minus 2. So I'm going to move those to the right, and I'm going to move the Laplace of y from the right to the left. So here on the left, I still have s Laplace of y. And now I'm going to subtract 0.1 Laplace of y. And remember, we're thinking about Laplace of y as a variable. It's like x. We're solving for x here. And we're going to move the minus 1 to the right. So it's going to become a plus 1 and add 1 over s minus 2 to the right. And here we go. Here's what we have. So to isolate Laplace of y, I'm going to factor it out. And I'm going to be left with s minus 0.1 equals 1 plus 1 over s minus 2. So that's going to give me Laplace of y equals, and I'm going to divide both sides by s minus 0.1, so that 1 will be over s minus 0.1, and the 1 over s minus 2 will be over s minus 0.1. Now, remember, this is really a fraction divided by s minus 0.1 over 1, so I can multiply by the reciprocal, but the real quick trick here is that the s minus 0.1 is going to multiply with the s minus 2 in the denominator. So I'll have Laplace of y equals 1 over s minus 0.1 plus 1 over s minus 2 times s minus 0.1. Now, just like in the previous problem, I see here in the denominator that I have a product of s terms, of s components, and so here I'm going to use partial fraction decomposition in Wolfram alpha to split this apart into something over s minus 2 plus something over s minus 0.1. So if you do that, the first term is okay, right? This is sort of our cleanup step now, where we're just trying to get everything to become invertible, so it's easier to see. We have 1 over s minus 0.1. And then in Wolfram alpha, if you do this, you get plus about 0.53. There's more decimal places, but we're just going to round to 2. S minus 2 in the denominator minus 0.53 over s minus 0.1. So in the previous video, I mentioned that these values aren't as predictable as they might seem. It depends on these values in the denominator. So make our lives a little bit easier here. I see that I have two like terms. I have one copy of 1 over s minus 0.1 here, and then I have negative 0.53 copies of 1 over s minus 0.1 here, so I can combine the numerators there since these are just fractions. And 1 minus 0.53 comes out to 0.47 over s minus 0.1 plus 0.53 over s minus 2. Now I'm ready to invert both sides. This is my last step. So in my last step, I am going to take the inverse. So I'm going to just go ahead and do it up here. We're going to take the, well, let's write out one more step. So the Laplace inverse of the left, and we have to do the same thing to both sides. So the Laplace inverse of 0.47 over s minus 0.1 plus 0.53 over s minus 2. Now the inverse Laplace of the Laplace of y is just going to give me back y. The inverse and the Laplace cancel each other out. And now I could use the linearity and factor out the constants to get 0.47 Laplace inverse of 1 over s minus 0.1 plus 0.53 times the Laplace inverse of 1 over s minus 2. Now I recognize these from our sheet. When we have 1 over s minus a constant, that is e to the opposite sign of that constant to the t power. So this one will be 0.47 e to the positive 0.1 t. So easy way to just quickly remember is that whatever this sign here is, the exponential will be the opposite sign. And here I'll have plus 0.53. My a is 2, so I'll have e to the 2t. And we're done. That's our final solution. We've solved this with Laplace transforms. Again, a nice thing to note here is that we get to plug in our initial condition while we're working the problem. So we don't have to go back and do that later. And that's it.